Really fundamental, a property that's, well, it's under everything. From the tiniest particles to the forces shaping the cosmos.
Yeah, we're getting into electric charge. We've got this detailed analysis you shared looking at particle charges.
And our mission today is to pull out the key insights from that material just for you. We want to unpack what electric charge really is.
And some of its, surprising properties, how it defines particles, builds atoms, molecules, and why, honestly, you can't really grasp physics without it, or chemistry, or even the universe itself.
Okay, let's do it. So the source material starts right at the beginning.
Oh.
What is electric charge?
It calls it a fundamental physical property of matter. Think of it like mass, maybe. Mass tells matter how to react to gravity.
And charge tells matter how to react in an electromagnetic field.
Right, exactly. And not just react to them, but it's the source of those fields, too. It's behind, well, all of it. Electricity, magnetism, even light.
It goes way back, doesn't it? Like static electricity, rubbing stuff together.
That's where the idea of two types first came from, positive and negative, attraction and repulsion.
Simple enough. But diving deeper, the analysis highlights some really non-obvious properties. What's the first big one?
Okay, so one of the most mind-bending ones, quantization.
Quantization, meaning?
Meaning charge isn't continuous. You can't just have any amount. It comes in these tiny, discrete packets, like little building blocks.
Yeah, so there's the smallest possible unit.
Yep. We call it the elementary charge. It's incredibly small, something like 1.602 times 10 to the minus 19 coulombs, a ridiculously tiny amount.
Wow. How did anyone even figure that out? Prove it wasn't just a smooth flow.
That was Robert Millikan. His oil drop experiment back in 1909. Genius, really.
The oil drop experiment. Refresh my memory.
He watched these tiny charged oil droplets floating in an electric field, and he measured their charges meticulously.
And
found that the charge on any droplet was always a whole number multiple of that fundamental value here. Never 1.5 times E or 0.7 times E's. Always 1E, 2E, 3E. Like that.
Direct proof. Wow. Okay, but wait. What about quarks? The source mentions quarks having fractional charges, right?
Right.
Like plus O(n) a t.
Yes. Yeah. That's a super important point. Quarks do have these fractional charges.
So doesn't that break the quantization rule?
You'd think so, but no. And the reason is something called color confinement.
Color confinement. Sounds colorful.
Yeah. It basically means you never, ever see a quark by itself. The strong force holds them together so tightly inside particles like protons and neutrons, you just can't isolate one.
Okay, so they're always bundled up.
Always. And when you add up the fractional charges of the quarks inside any observable particle, anything you can actually detect freely, the total always comes out to an integer multiple of E, like 0 plus EE.
Ah, got it.
Yeah.
So the individual quarks are fractional, but the packages they come in follow the rule. Clever.
Exactly. So quantization holds for anything we can actually, measure directly.
Okay, property one, quantized. What's another big law from the analysis?
Conservation. This one's huge. The net electric charge in an isolated system never changes. It's constant.
Meaning you can't just create charge out of nothing?
Yeah.
Or destroy it?
Pretty much. You can move it around, transfer it, or if you create new charged particles, like from pure energy, they always appear in pairs with equal and opposite charges. Like a photon, which is neutral, can turn into an electron, E, and a positron plus E.
Ah, so the total charge starts at 0 and ends at 0, E plus plus E. The balance sheet is always balanced.
Always. The universe keeps strict accounts when it comes to charge.
Okay. And the basic interaction? Still the same old rule?
Still the same. Likes repel, unlikes attract. Simple but powerful. Coulomb's law describes the force precisely depends on the charges involved and how far apart they are.
Now, the source mentions something really weird. Relativistic invariance. What on earth is that?
This is fascinating. And it's different from, say, mass in relativity.
How so?
A particle's electric charge doesn't change no matter how fast it's moving.
Seriously. So an electron sitting still has the same charge as one, going at like 99% the speed of light.
Exactly the same charge. Its mass increases, time slows down for it, but its charge, constant. It's a Lorentz invariant.
That is counterintuitive. Charge is just fixed. Huh. And the unit we use?
The SI unit is the Coulomb, capital C.
Right. And how's that defined?
It's tied to electric current. 1 Coulomb is the charge that flows past a point in 1 second if the current is 1 ampere.
Okay, so 1 Coulomb equals 1 ampere second.
Yep. And remember that elementary charge checked, it's about 1.602 by 10 RO coulombs. So 1 Coulomb is actually a massive number of elementary charges, trillions and trillions.
Okay, let's recap the properties. Quantized, conserved, interacts via like-unlike rule, relativistically invariant, measured in coulombs.
Got it. Now, how does this help us classify the fundamental particles, the really small stuff?
Charge is absolutely key for that. It's one of the main ways we sort particles in the standard model. It tells us a lot about how they'll behave.
Let's start with the leptons. What are they again? Leptons are the ones that don't feel the strong nuclear force. The most famous one, of course, is the electron.
Our old friend, electron. Charge E, powering everything.
That's the one. Forms atoms, makes currents flow. Then you have its heavier cousins, the muon and the tau.
Also charge U.
Also charge U. Just heavier and unstable. They decay quickly.
Okay. And the neutrinos.
Ah, the neutrinos. One type for each electron, muon, tau. And they are electrically neutral charge.
The ghostly ones. Super light, barely interact.
Exactly. Only feel the weak force and gravity. And importantly, for all these leptons, there's an antiparticle.
With opposite charge.
Opposite charge.
Yeah.
The electron's antiparticle is the positron, charge plus E, antimuon plus E, antitau plus E, antineutrinos. Well, they're still neutral. Charge 0.
Got it. Okay, now for the quarks. The ones that do feel the strong force, this is where the fractions come in.
Right. Quarks carry these fractional charges. We group them into 2 types based on charge.
Which are?
The up-type quarks. That's the up charm and top quarks.
Yeah.
They all have a charge of plus U.
Plus 2/3 E.
Okay. And the down-type quarks. Down, strange, and bottom. They all carry a charge of U.
Minus 1/3 E. And they have antiquarks too.
They do. With the opposite charges, anti-up is U, anti-down is plus U, anti-charm is U, and so on.
But again, we never see these alone because of
Color confinement. Yep. They're always stuck together inside other particles.
Which brings us nicely to those composite particles. Hadrons, made of quarks.
Exactly. Hadrons are quark combinations bound by the strong force. 2 main families, baryons and mesons.
Let's do baryons first. They're made of
3 quarks, or 3 antiquarks for antibaryons.
like protons and neutrons, the stuff inside atomic nuclei.
The very same. The source spells out their recipes. A proton is 2 up quarks and 1 down quark, so U.
Okay, let's add it up. Plus UV plus UV plus E comes out to exactly plus E. That's the proton's charge.
Makes sense. And the neutron.
1 up, 2 downs. U, so plus UE plus E.
0. That's why it's neutral. Cool. Right. And the analysis notes there are other baryons too, like lambda, sigma particles, different quark combos, but they always end up with an integer charge.
Yeah.
Plus E, 0, E, etc.
Okay, and the other family? Mesons.
Mesons are different. They're made of 1 quark and 1 antiquark.
Matter and antimatter together. Example.
Pions are common ones. A positive pion is an up quark and an anti-down quark. Remember, anti-down has charge plus U.
So up plus E plus anti-down plus E equals plus E.
Perfect. And a negative pion. That's an anti-up quark and a down quark.
Adds up to E.
You got it. And a neutral pion is usually a mix like a ponti-up or down anti-down, canceling out to 0 charge.
The source mentions kaons too.
Yeah, like Kui is an up and an anti-strange, charge plus E. Curie is a down and an anti-strange, charge 0. Lots of combinations, but always yielding integer charges because of that quark plus antiquark structure.
So the charges of matter particles, fundamental or composite, seem well defined. What about the particles that carry the forces? The bosons.
Their charges are super important too. Let's start with the photon.
The carrier of the electromagnetic force itself. The force caused by charge. Its charge must be
0, which is kind of interesting, right? The mediator of the force generated by charge is itself chargeless?
Huh. Yeah, it is.
Yeah.
Okay. What about gluons? Strong force carriers.
Also charge 0, electrically speaking. They carry color charge for the strong force, but no electric charge.
Now, the weak force carriers are different, aren't they? The W bosons.
Yes. The Wan and Wa bosons, they are unique among the force carriers because they do carry electric charge, plus E and E respectively.
And the source highlights that this is really important for what they do.
Absolutely crucial. Because the W bosons are charged, they can actually change the charge and the type or flavor of other particles when they interact.
How does that work?
Think about a down quark turning into an up quark plus E. That's an increase in charge of plus D. How does it happen? The down quark emits a Y boson.
The WAR carries away the E charge, leaving the quark with plus E more charge than it started with. It balances the books.
Exactly. It's fundamental to processes like radioactive beta decay. Then there's the Z boson, Z-war.
Also weak force.
Also weak force, but like the photon and gluon, it's neutral, charge 0.
And the Higgs boson. giving particles mass.
Also charge 0. Seems like being electrically neutral is pretty common for bosons, except for those Ws.
Okay, so we've covered charge at the fundamental level. How does this scale up? How does it work in the atoms and molecules we actually, interact with?
Right, let's build back up. Atoms normally are electrically neutral because they have a positively charged nucleus made of protons plus E and neutrons, 0, surrounded by a cloud of negatively charged electrons, E. And in a neutral atom, the number of electrons exactly matches the number of protons.
So the positive charge in the middle is perfectly canceled by the negative charge buzzing around it.
Right.
Like helium, 2 protons, 2 electrons. Net charge, 0.
Precisely. The atomic number tells you the number of protons, and in a neutral atom, that's also the number of electrons.
But atoms don't always stay neutral, do they? They can become ions.
Exactly. If an atom loses 1 or more electrons, it has more protons than electrons left, more positive charge than negative.
So it becomes positively charged.
Yeah.
Attication.
That's right. Like sodium, losing an electron becomes no U, with a net charge of plus E.
And if it gains electrons,
then it has more negative charge than positive. It becomes negatively charged. And an anion, like chlorine, Cl, gaining an electron becomes Clo, net charge E.
Okay, that makes sense. And then these atoms, charged or neutral, bond together to form molecules.
Yep. And most molecules you encounter every day are neutral overall. Water, Keo, Euro, sugar. The total positive charge from all the nuclei equals the total negative charge from all the electrons.
But not always. Can molecules have a net charge?
Definitely. We call those polyatomic ions. Think of sulfate. SO, that whole group of 1 sulfur and 4 oxygen atoms carries an overall charge of -2e. Or ammonium, NH0, carries a charge of plus E.
Right. But the source also mentioned something called polarity, even in neutral molecules.
Yes, this is super important. Even if a molecule's total charge is 0, the charge might not be distributed evenly within the molecule.
How does that happen?
Often because some atoms in a bond pull electrons more strongly than others. This creates partial charges, like little positive and negative patches on the molecule. Or the molecule's shape might lead to an uneven distribution.
And the classic example is water, Ha.
The perfect example. Oxygen pulls the shared electrons much more strongly than hydrogen does.
So the oxygen end of the molecule is slightly negative and the hydrogen ends are slightly positive.
Exactly. Even though the whole molecule is neutral, it has these charged ends. It's polar.
And why does that matter so much?
Oh, it's huge.
Yeah.
It dictates how molecules interact. Polarity is why water is such a great solvent. The positive ends attract negative ions. The negative ends attract positive ions. It explains surface tension, boiling points. So many properties depend on this subtle charge distribution. It's fundamental to chemistry and biology.
So charge isn't just about net +1 or -1. It's about the distribution, too.
Okay. Now, the analysis broadens the term charge. It talks about other types of charge in physics. What's going on there?
Yeah, it's interesting. Physicists sometimes use charge more generally. It can mean any conserved quantity that acts as the source for a fundamental interaction.
So electric charge is the source for the electromagnetic force.
Right. And for the strong force, the source is called color charge.
Which we mentioned with quarks in confinement.
Exactly. Quarks have color, red, green, or blue. Antiquarks have anticolor. Gluons, the strong force carriers, have anticolor combinations. It's analogous to electric charge, but for the strong force.
And the rule is that hadrons, the observable particles, have to be color neutral or white.
Correct. The colors have to combine in a way that cancels out, like red plus green plus blue in a proton, or red plus anti-red in a meson.
Fascinating. And the weak force, does it have its own charge? It does, in a way. There are quantum numbers called weak isospin and weak hypercharge. They're conserved quantities related to how particles interact via the weak force.
So analogous concepts for each force.
Pretty much. And they're actually connected. The source mentions a formula, Q equals I plus YW2.
What's that?
It links a particle's electric charge, Q, to its weak isospin, specifically the third component, and its weak hypercharge, YW. It shows there's a deep relationship between the electromagnetic and weak forces, unified as the electroweak force.
Wow. Okay. So bringing this all together then, why does charge matter so profoundly? What's the big picture takeaway from the analysis?
It's almost everything, really. First, the structure of matter.
Atoms and molecules.
Exactly. The positive charge of the nucleus determines what element an atom is. The attraction between that nucleus and the negative electrons holds the atom together. Chemical bonding. That's all electromagnetic interactions driven by charge.
Second, obviously, electromagnetism.
The source of it all. Electricity, magnetism, light, radio waves all stem from charge, moving or static. Our technology, natural phenomena, it's all charge in action.
Third, you mentioned fundamental interactions.
Yeah, a particle's charge is electric, color, weak, determine which forces it feels and how strongly. It's like its interaction profile.
Fourth, the conservation laws.
Absolutely bedrock. Charge conservation lets us track what happens in particle reactions. The total charge always stays the same before and after. It constrains what's possible.
Fifth, its role in the Standard Model.
It's deeply connected to fundamental symmetries, called gauge symmetries. These mathematical structures are the foundation of how we describe the forces. Charge fits right into that elegant framework.
And finally, the really big scale, cosmology.
Yeah, the fact that the universe appears to be electrically neutral overall is incredibly important.
Why is that?
If there was even a tiny imbalance, the resulting electromagnetic forces would be vastly stronger than gravity, like unbelievably stronger. Stars wouldn't form, galaxies wouldn't hold together, the universe would look completely different.
So the early universe must have produced matter and antimatter in almost perfect balance, charge-wise, with just that tiny bit more matter left over.
Something like that. Ensuring overall neutrality was crucial for the universe to evolve the way it did.
It really is central then, from quarks to cosmos.
Couldn't have put it better myself.
But despite all we know, the analysis points out there are still big questions. Mysteries about charge we haven't solved.
Oh, absolutely. Deep ones. Like, why is charge quantized? We know it is. Millikan showed that. But what's the fundamental reason?
Is there a theory?
There's a fascinating theoretical link. It involves hypothetical particles called magnetic monopoles.
Magnets with only a north pole or only a south pole.
Kind of, yeah. If just one magnetic monopole exists anywhere in the universe, quantum mechanics predicts that electric charge must be quantized. It's called Dirac's quantization condition.
Whoa. So finding one monopole would explain charge quantization? That's wild.
It would be a monumental discovery. Another question is, could there be other kinds of charges linked to forces we haven't even discovered yet? Theories beyond the Standard Model play with these ideas.
And then there's the one that the source really emphasizes, the proton-electron charge equality.
Right. Why is the proton's positive charge exactly equal in magnitude to the electron's negative charge? QE will exist, euro.
It has to be for neutral atoms to exist, right?
It's absolutely essential for chemistry, for life, for everything we see. If they were off by even a tiny fraction, atoms wouldn't be neutral, and electrostatic forces would dominate everything.
But why are they equal? One's a fundamental particle, electron. The other's a composite bag of quarks, proton.
Exactly. The Standard Model just puts this equality in by hand. It doesn't explain the underlying reason. Why does this complex thing have the exact opposite charge of this simple thing? It's a profound mystery. Maybe it hints at a deeper unification of particles and forces.
So quite a journey. From static cling to quantum fields, fractional quarks, composite particles, chemistry, cosmology, all tied together by this property, charge.
It's not just a static label. It's the engine of interaction at almost every level.
And maybe the final thought to leave you with, drawing from this analysis, is to really consider that incredible precision. That perfect balance between the electron's charge and the proton's charge.
What fundamental truth about how the universe is put together is hiding inside that exact equality?
Something to ponder. Thanks for taking this deep dive with us.
Always a pleasure.